Hey chemistry crew, Mr. Collier here. I wanted to go over pages 18 to 19 in your gases packet. A lot of pretty straightforward stuff here, but a couple new things. So first we got some definitions at the top. The pressure of a gas is inversely related to its volume. So pressure and volume, that is going to be Boyle's law. It's not super important that you memorize the names of the laws, especially here as we're just trying to kind of get through this content. But what I do want you to know is be able to look these up and reference them. Number two here, the sum of partial pressures is equal to the total pressure. That's Dalton's law. Dalton is the one that's like a little bit different, right? Because now we're talking about pressures and adding them. We're not talking about different variables, just pressure. Equal volumes of gas contain equal numbers of particle. That's Avogadro's law. And the fourth law here, the volume of a gas is directly proportional to temperature. So volume and temperature, that is Charles' law. Next up, we have some some graphs, and these graphs show different relationships. We have a positive or direct relationship, we have an inverse relationship, and we have this sort of no relationship, just a constant relationship. So the first one here is actually the trickiest, gas pressure and its temperature. Okay, so as you heat a gas, its pressure goes up. That is direct. That's why it would be there. The relationship between volume and pressure, so that is inverse. If I compress a gas and make it take up less volume, its pressure is going to go up. So that's inverse. This one goes down, the other goes up. Temperature and volume, as you heat a gas, it goes up. So that's another positive relationship. And volume and molar mass, there's no relationship there. That's that Avogadro's law, that those are not related. All right, then we have a little section of increase, decrease, remain the same. So as a gas is compressed, so picture squeezing something, right? The distance between the gas molecules decreases. They get closer together because of the extra pressure that you're applying. But the number of gas molecules stays the same, right? Squeezing something to make it smaller doesn't change the particles that it's made of or how many of them there are. The volume decreases, again, because you're squishing it, making it take up less space. The pressure is going to increase. Pressure is related to how many collisions occur. And so if you make it take up less space, there's going to be more of those collisions happening. Its density is going to increase because density is mass as it relates to volume. And if the mass stays the same, but the volume gets smaller, you're going to have something that is more dense, more tightly packed. And its mass, again, that's the particles it's made out of, is going to stay the same. All right. Moving on then, that was 18, this is now 19. Standard temperature is 0 Celsius. Absolute zero is 0 Kelvin. I'll say a little bit more about that down here on 21. The volume of 1 mole of any gas at standard temperature is 22.4 liters. That actually is from a different chapter, and it's coming back now that we're talking about gases. Standard pressure is equal to, and notice that the units here are kilopascals, so I chose 101.325. That's the number that goes with kilopascals. That's also 1 atmosphere. The pressure of 2 liters of a gas doubles, so its new volume would be 1 liter. So this is relating pressure to volume. So if we are doubling the pressure, the volume would be half. If the Kelvin temperature doubles, the new volume would be, so this is doubling temperature. I highlighted too much right there. Temperature, and we're looking at volume. Oh boy, those are directly related. So as I double, this is going to double as well. How did Charles know that the behavior of gases at very low temperatures when he could not experiment with temperatures below freezing? So the way that you do this is you do a graph and you extrapolate it backwards. And that's where we discovered that absolute zero would be that temperature where all molecular movement ceases. The volume is 0 theoretically, right? And that's why these laws kind of fall apart at these really cold temperatures. More on that coming up later in the chapter. Finally, we have 2 sample problems. We're going to use gas laws to do some calculations here. We are looking at a temperature, all right, and a volume. So we need the equation that relates temperature to volume. So that's V1T1 over V2T2. So it's 200 mils when it's at room temperature, all right? Notice the word empty is in quotes. Even when you've emptied out a can, it still has some sort of gases in it. And so we want to know the volume at this new temperature, this 800 degrees Celsius fire. Notice that both of my temperatures don't match what's in the problem. That's because I've converted them to Kelvin by adding 273. Cross multiply, solve for V, and you'll get 727. Excuse me. And the very last problem here, we've got a volume and we've got a pressure, right? It's a balloon that's released at sea level where the pressure is 1 atmosphere. And then it's going to rise up into the atmosphere. And this is something that happens, right? If you put a weather balloon and you release it high into the atmosphere, as it gets higher up, it gets colder and there's less pressure. And so it's going to expand. So what new volume is that going to reach? So we know its starting volume and its starting pressure. I cheated and put 1 atmosphere, but you could have just left it 101. And we want to know what the new volume will be when that pressure goes up to goes down to 8 kilopascals. Again, divide, solve for your answer, and our new volume is going to be a little over 50 liters. So it expands quite a bit. So those weather balloons need to be able to stretch lest they pop. And I think they will actually start to deflate through effusion, which is something that'll come up much later in the chapter. All right, that's it for this one. Let me know if you have any questions.